Good evening, everyone. It's my pleasure and privilege to welcome all of you for today's webinar, jointly organized by the TCS Research, along with ACM India Council and ACM Special Interest Group on Computer Science Education's Indian counterpart, iSIGCSE chapter, on a highly relevant and significant topic, Computational Intelligence at Edge. I am Chitra Babu, Chair of ACM India iSIGCSE, also Professor at the Department of Computer Science and Engineering at SSN College of Engineering, Chennai, and would like to briefly tell about the activities of ACM India and the iSIGCSE chapter. You can see ACM India at a glance on this slide. As an ACM member, you will be part of the world's largest computing professional society. Out of the 1 lakh members worldwide, about 11% of them are from India and half of them are students. ACM India is spread across the country mainly due to its chapters. The chapters get access to ACM's Distinguished Speaker Program and ACM India's Eminent Speaker Program. You can invite any expert from these programs and ACM will take care of the travel. These programs are now also available on the virtual platform. ACM India organizes summer and winter schools for the students in different emerging research areas in computer science for the past 3 years. Faculty for these schools is drawn from prominent academic institutes and industry. ACM has taken other education initiatives such as Teaching Partnership Program, through which faculty from eminent institutes or professionals from industry teach courses along with the faculty in charges at the local institute. ACM also has taken very good research initiatives such as PhD Clinic, where the PhD students get an opportunity to discuss their research with faculty and industry researchers who act as sounding board and provide useful suggestions. We have something special for promoting gender diversity too, ACMW, which works for empowering women in computing. It has several initiatives for female students. It organizes Lady Ada programming competition, national level hackathon, grad cohort, a forum meant for graduate students, and one of the summer schools all exclusively meant for girl students. ACM India has instituted 3 prestigious awards, one for outstanding contributions to computing education. The second is for early career researcher, presented to individuals in their early career who have made outstanding contributions to computing while primarily working in India. The third award is for outstanding contributions in computing by a woman who has made significant contributions in computing. The primary objective in the ACM of the ACM iSIGCSE chapter is to bring academicians and industry researchers together to discuss and disseminate research related to computing education and best practices related to curriculum design, pedagogy, and assessment. This year, the annual Compute Symposium organized by ACM India and iSIGCSE is going to be held with the approval of ACM in cooperation with SIGCSE during November 2nd to 4th. We are also in the process of getting approval for publishing the proceedings of the symposium in ACM Digital Library. I would urge everyone who has joined today for this webinar to consider becoming an ACM professional member for a nominal fee if you are not one already. The membership for iSIGCSE is free. Consider joining us to contribute towards improving the quality of CS education all over India. Thank you.
Thank you, Professor Chitra. So I think now we'll move into the actual webinar. So as we know that the topic of the webinar is a kind of very relevant computational intelligence at edge. And so Sharnava, can you make it full screen?
Arpan, just one thing. I'm seeing a little gray square or rectangle obscuring the slide. Is it just me or is it
everyone? I think, Sharnava, I think you have to move that. Can you just move that window? It is the video window, I think. You have to minimize that window. Yeah, okay. Something like that. It should be okay. I think this should be okay. Yeah, okay. But Sharnava, we cannot see the screen now. The PPT. Okay. Okay. I think it should be fine. Okay. So can we go to the first one? No, no, no. Shana, we are seeing the last screen. Can you stay in the second? Just go to the next one. No, I don't know what is that. Okay. So I think, sorry for that. Yeah. So we are as we know that the topic is computational intelligence age, and it is very relevant topic today, as Professor Chitra was mentioning. And if you think of that history, that IoT, when it started with the data ingestion at the edge and data visualization at the cloud. That's what was the IoT's promise that it started. And then over the years, in recent year, it moved into the place where the data ingestion was happening in the edge and the analytics and intelligence was happening in the cloud. That was the next phase of IoT. And now we are in an era where actually we are now talking at that even the analytics and intelligence will be also moving into the edge in addition to that ingestion. And that is what is today's topic is about, what you mean by that and what are the challenges of this computational intelligence age. So we are very lucky to have a very elite set of speakers and panelists today. So we start with a talk by Professor Archan Mishra, and then we'll have a fireside chat and a panelist, and then we'll have a panel discussion, and then we'll have some Q&A. So Sharnav, if we just move to the next slide, just introduce the speakers. So yeah, so can you move to the next slide, Sharnav? Yeah. Okay. So we have in the panel, we have Dr. Venkat Padmanabhan. She is the Deputy Managing Director of Microsoft Research. And as you see that he is a very, very well acclaimed person in this field, and he has won the Santi Swarup Bhatnagar Prize and the Distinguished Alumnus Award from IIT Delhi, and also a fellow of INE, ACM and IEEE. I'm not good. So we are very lucky to have Venkat in the panel. We also have, can you Shana move to the next slide? So we also have Dr. Rijureka Sen, who is Assistant Professor in Computer Science Engineering in IIT Delhi. And as we know, she actually won that ACM India Doctoral Dissertation Award earlier, and her research area is very, very relevant to what we are going to discuss today. And as we move to the next one, Sharnava, can we move to the next one? So we also have Dr. Bala Murli, who is the Chief Scientist and Head of Robotics and Autonomous Systems Research Area in TCS. And he is the TCS Distinguished Award winner earlier, and he also is a serial innovator. So he is a serial innovator award winner from Tata Group. So we are really lucky to have him, and then we'll listen from him also. So these are the three panelists that we'll have. And then finally, let me introduce Professor Archan Mishra, who will be our keynote speaker. And we'll start with his talk. So he is the Vice Provost Research and Professor of Computer Science at SMU in Singapore. And he's a very well acclaimed researcher in this field and in the area. So, and today, currently, he is looking into the ultra low energy execution of machine intelligence algorithms on wearable and IoT devices. So, it is a very, very relevant thing that we're going to hear from him today. And he's already ACM distinguished member. So, I think with that background and introduction, let us move into the actual talk. And I'll just invite Professor Archan Mishra to start his talk. And as he starts presenting his talk, and yes, so I just request the audience to, we'll have a formal Q&A session at the end, but it will be very good if we can actually make it more interactive and start posting all your questions as and when you have it into the chat box. We have Professor Archan's student, Ila, is already there. So some of the questions she will be able to answer there. Or if something is not there, can be there, so Archan can take it up later. But don't wait for the end to post the questions. Please start posting the questions as we see that slides and make it more interactive. That is my request to the audience. So over to you, Archan. Thank you.
All right. Well, thank you, Arpan. And first of all, my thanks also to Dr. Chitra for the invitation and for ACM India for organizing this event. It's also a pleasure to have Venkat and Riju on as co-panelists, people I know very well for a long time, and Dr. Bala as well, whom I've known for a very long time. So I've got approximately 40 minutes to be presenting today. So I'm going to try and wrap up by about 35 to 37-minute mark. The title that I called, edge computing, I think broadly all the attendees sort of understand the power of it, which is the ability to take data that is produced by sensors right at the edge of the network from pervasive devices, from cameras, IoT devices, so on, and to process it and extract insights from it right at the edge instead of transferring it over the cloud. So within that broad parameter, I'll be talking primarily about this notion of collaborative machine intelligence. This is sort of a self-coined term, if I may, but it's the idea that devices which are executing their own DNN or deep neural network pipelines, they need to be sharing state among themselves or sharing intelligence and control parameters with the sensors themselves. So really two big ideas. One is that if you have multiple DNN pipelines, they should actually be sharing intermediate state with one another so that it improves something, and we'll see what that something is. Either improves energy efficiency or improves accuracy or reduces latency and so on. The other idea is that the DNNs that are executing are not just passive recipients of data from the sensors, but depending on the outputs or the inferences made by the DNNs, they actually go back and influence the operation of the sensors and some parameter settings in the sensor. So I wanted to acknowledge several PhD students, postdocs, research engineers, and collaboratars, several of them were faculty, and many of them that you know, who've all been part of this journey over the last 3-4 years. So very briefly, what I wanted to do is just to give you a sense of where I'm coming from. Here is my own created roadmap of my research over the last 10 to 11 years. So I joined SMU in Singapore in 2010, and for the first 5 years, I did what I'd consider mobile sensing and analytics, which was the ability to look at sensors on mobile devices, smartphones, and maybe wireless infrastructure networks, and really try to extract insights from them, such as, they were mostly what I call locomotive insights. So how you are moving, are you sitting down, are you climbing stairs, physical activities like that. So after that, starting around 2014, it's a journey that many people will be familiar with. The device of choice or interest moved from a smartphone to wearable devices, and primarily I focused on smart watches or wrist-worn devices with a little bit of work around smart glasses, which was also the rage around 2015 or so. And the key difference when you move from the first phase to the second, the two key differences. One is the types of context or activity you can sense. Because these are attached to your limbs or your head, you can extract things such as that are based on gestures, such as eating or exercising in the gym and so on. But the other big difference was that approximately speaking, the battery capacity of these wearable devices is 1/10, 1 order of magnitude lower than the battery capacity of the smartphones. So about 300 to 400 milliamp hours compared to 4,000 milliamp hours. So what that means is the focus progressively shifts towards not just improving accuracy, but dramatically reducing energy efficiency. And over the last 3 years or so, I would say, and that's the two main highlights of the right side, on reflecting on my own research, I believe that if you want to make those dramatic progresses in pervasive deployment of IoT devices, we really eventually have to move to making them either ultra low power or even battery less. In other words, work purely on energy harvesting, which is an enormous challenge in terms of doing it on scale. And I'm very, very in the early stages of this research journey. But the method that I wanted to talk about, sorry, I don't know if this screen obscures it, it's to utilize a combination of different sensing modalities and also do this collaborative machine intelligence at the edge. So those are the two things that I'll briefly talk about. It'll be a breadth first exposition of a few different projects that I wanted to cover, several of which are unpublished and ongoing work. So I wanted to just really present the bleeding edge of some of our group's work in this space and really welcome the opportunity to hear feedback and questions from you all. So with that background, okay, I just want to make sure. So one quick primer, because I understand that the audience is quite disparate and broad. I mean, we have very accomplished professors to whom this is old news, but there are probably many students and many engineers, professional engineers who may not essentially be aware of how the world is shifting. So the slide on the left, the figure on the left is a classic slide which shows that how Moore's law has transformed things such as disk capacity, CPU speed, primarily disk capacity, which is just phenomenal, the advances in sort of storage density. The one thing that has not transformed at exponential speed is battery energy density yet. And the other point that I wanted to make, again, these are just infographics from the web. In 2019 or 2018, apparently, 80% of the data generated on the internet, data generated from doorbell cams and baby monitors and traffic cameras, 80% of it hits data centers. But by 2022, which is this year, this was the prediction, the story shifts dramatically. 70% of the data generated does not hit a data center. It gets consumed and discarded at the edge. So this is a dramatic transformation. And through my own journey, the one thing I realized was, I used to work a lot in mobile wearable sensing, and I realized that really to achieve the vision of pervasive, practical sensing, you needed to combine infrastructure sensing with mobile sensing. And that's where the edge plays an important role in terms of sort of looking at the ability to orchestrate the activation of these energy efficient mobile or wearable sensing devices. The other piece, and this is certainly a thought process that I've been championing for the last few years, and it's again very much a work in progress. For a decade we worked on the assumption that computation is inexpensive and communication is orders of magnitude more expensive in terms of energy. So we would always want to process and discard a byte rather than transmit it wirelessly. Now, I think the general statement is still true. However, sort of the scales of the disparity have reduced fairly significantly for the following reasons. One, we're beginning to see lots of sort of ultra low power, short range technologies, things like LoRa, et cetera, which is long range. But as sort of coding efficiency improves, the ability to transmit small amounts of data at low power has increased significantly. The other aspect is, the computation per byte or bit or flops itself has reduced in power, but the typical inferencing pipelines, now we talk these deep neural networks with 200, 300 layers in it, that has exploded, again, more than exponentially. So if you take a video data, it is no longer as clear-cut that it is always more efficient to run the DNN algorithm on the video data, extract, say, the object detectors on it, and transfer only the detected objects versus transferring the raw video frame or a compressed video frame to an edge device where it's processed. So that paradigm shift is important because I think what it allows us is it sort of accentuates, my belief in this notion of collaborative machine intelligence, because sharing small bits of what I call digests or small bits of intermediate state between DNN pipelines can actually dramatically transform the ability of these pipelines to improve their own processing accuracy or efficiency. And so those are two sort of big picture concepts that I wanted to articulate. Because it's a broad-based topic and presentation, I want to give a very brief primer, not on my own work, and I'll do this in ideally less than 3 minutes. There's been a lot of work on edge computing, and I use object detection as a case study. So some classic work, and you'll see the references. So one is sort of early exit strategies, where you don't execute the whole DNN. If you're certain, even at the initial stages, that the object you're detecting has high confidence, you can exit early. So it's sort of runtime reducing the latency of the processing. So the next piece, of course, is that you do DNN slicing. So you partition the DNN execution. Some of it you execute on the device, on a camera node, and some of it you offload to the edge. And there have been a lot of work on best ways to execute, partition this, and best ways to compress the state when you transfer the intermediate state from layer I to layer, which is executing on, say, the camera or a mobile device, to layer I+1, which is executing on the edge node. So this is, again, it's sort of this cloud offloading with sort of a breakpoint in between. Now, there's also approaches that look at modifying the DNNs, and I'm just giving you, I mean, you'll see the references. I'll be happy to share the slides. But modifying the DNN, there's sort of runtime neural pruning or model merging. So model merging says you have 2-3 different DNNs executing on the same data with different tasks. So one doing object detection, another doing face recognition, for example. Can you combine them and create a single global model? So instead of having 2 DNNs, you have a single DNN that reduces the memory footprint and the execution latency. And similarly, you have things like spatial sparsity masking, which is the idea that to improve the execution efficiency, you know, the whole image, maybe only 30% of the image has objects of interest. So you isolate those parts and you execute the convolutional layers and extract the feature maps only on those parts selectively. And you do that on a per instance, per image basis. Again, there's some references over here. And finally, there is various approaches that look at optimizing the processing at the edge. So there's work, you know, such as Chameleon, which looks at determining sort of as the content in the video stream changes, it's determining what's the right frame rate, what's the right resolution, what's the DNN parameters. And, you know, it's looking at the trade-offs between constantly changing this versus doing this periodically. So I'll talk about some of my own work today, which is number 2, which is going to be looking at modifying the input itself, again, to save energy on the pervasive device. Okay, so that was sort of in a nutshell the brief background. What I want to get to now is 2 different pieces of work. I'll come to the edge analytics, which is really the core of this work, but I first wanted to talk a little bit about why the edge needs to do things in real time, not just to do deductions and insights, but actually modify the operation of the pervasive devices. So I mentioned about building battery-less sensors. So one of the pieces of work that I wanted to highlight that we had done was we built a battery-less wearable device, a wrist-worn wearable. I won't call it a wristwatch, but it had a wrist-worn form factor. And the way it was charged, it had a supercapacitor and was harvesting energy only from Wi-Fi access point transmissions. And this could work within the range of like a meeting room, but the device had an accelerometer on it that would collect and transfer the accelerometer data, thereby enabling you to keep track of gestural activities. And the way it worked, the basic idea was that somebody wearing it would come into the room, send a single packet, so you needed very little energy. And after that, the access point would beamform its transmission. So instead of transmitting just data packets, it's a regular access point, it would beamform transmissions and transfer them over, which you know, would be harvested by the wearable device, stored, and then whenever the person made a movement, there'd be a kinetic energy harvester-based trigger that would turn on the accelerometer infrastructure, collect the data, and transfer it back. So the challenge, if you look at the bottom right, is we know wireless energy harvesting is, you know, it exists. But the reality is, if you look at the omnidirectional transmitters in, you know, the conventional access points at home, at a distance of about 1.5 meters, you harvest less than a microwatt of power. So that's not very efficient and effective. So we built some of the hardware. We used a warp board to model an 8-antenna Wi-Fi. And again, I'm skipping a lot of the details, but the real insight was that by doing that beamforming, we significantly increased the energy harvesting efficiency. So with 8 antennas at a distance of slightly over 1 meter, we were able to harvest about 250 microwatts of power. Now, 250 microwatts is still way less than a milliwatt, but it already begins to move the needle in terms of intermittent operation, because if you're not making gestures constantly, maybe you harvest with a duty cycle of 90%, and then 10% of the time the accelerometer turns on and you collect the data. And we actually showed that this work in sort of controlled user studies. You can see this PhD student working, and we were able to, what the graph shows on the right is we actually had a net energy surplus on 4 different users. So the energy spent in collecting the accelerometer data and transmitting it wirelessly over a narrowband radio was actually less than the energy harvested by this technique. So that's sort of a big picture, and we've expanded. We did work on this. Some of this was joint work with TCS, with Arpan's group over here, where the idea was that, you know, instead of just harvesting energy solely, we would use RFID tags, some tags worn by the user, completely passive, some tags mounted on objects. And the RFID scanner would be the ones powering these things. Now, the issue there was that a scanner could deliver large amounts of power only if it did beamforming, if it was directional. So the idea was we'd look for perturbations in the certain region of the space from the wireless readings being reflected back by the tags, and understand that the human being was moving in a certain region, and then selectively direct power to activate both the tags on the objects in that vicinity, as well as the tags on the human hand. And through this, what we found is we could track activities fairly accurately. You see the confusion matrix on the left. Again, this is a completely battery-less system based purely on passive Wi-Fi tags. Now, why did I present, and I will not dwell on this further, but some of the things we talked about, there was only one device in the room and only one Wi-Fi access point. But I think as one moves into the 6G architecture and so on, we're beginning to see distributed radio access networks. So lots of antennas distributed around the room. The challenge, of course, is you want to support multiple IoT or wearable devices. And that means that you either have to modify the beamforming algorithm, or you have to do time division, multiplexing, and serve different devices in turn, which reduces the overall energy per device. But one of the pieces of work that I wanted to point out that showed, admittedly in a very controlled lab setting, was this work on a Rutgers, which showed on the right the energy ball. You see this is the WinLab test bed. So they have all of these, I think, 900 megahertz radios. And by adjusting the phase on all of these, it's a very high density sort of access point like architecture. They were able to deliver about 1 milliwatt of power to any single point in the room. And you could control that by just changing the phases and the direction of the beams. So what this illustrates is as we move forward, there is really the possibility of introducing this ultra low energy mobile wearable pervasive systems. But to do this, you need to process the data on the edge in real time so that you can go control the parameters on these sensors. So that's the message I wanted to give. Now I move to the second part of my talk. I'm just watching the time. I think I should be done in about 15 minutes more. So this is the idea of collaborative machine intelligence. I'm using as an exemplar this notion of a campus-like place being monitored by cameras A, B, C, and D. And you can see that one of the things that you see A's view here, A can see the purple person, cannot see the green because it's obscured. B can see both of them. So the whole idea is that in some sense, if the DNN pipelines collaborate or we share the images as a starting point, we should be able to improve the accuracy of both systems together by taking advantage of the diversity of views, the different perspectives that they offer. I'm using just again, an object detection using video sensors as an exemplar. Now, there is a challenge over here, which is that anytime one brings in collaborative machine intelligence ideas, you're depending on peers to provide you some priors or some state. Now, if those peers are corrupted or malicious, they'll actually degrade your performance because you're relying on inaccurate data. So I wanted to upfront flag out that there is an opportunity, which is not really my area of research, but bringing in all the work on distributed reputation systems, outlier identification, etc., to filter out sort of these spurious states that may be generated by malicious or misconfigured DNN pipelines operating on some peer devices. So that's the basic background, but the core idea, again, of collaborative machine intelligence is somehow these guys orchestrate in real time. So let's look at the examples progressively. So I'm going to give you, I think, 4 different examples, 4 different projects, if you will, each one operating at a slightly different design point, in the design space. So I start with something that is, I would say, the most basic, nothing fancy at all, nothing very imaginative, if I may. So you have this idea that you have 2 cameras. This is a PETS data set, and each camera is processing its own DNN pipeline. It could be an SSD pipeline, for example. And what you can do is, because some parts of the image are overlapping, the other cameras that also operate and see the image, they can run their own object detector and pass you effectively black and white masks, where the masks, they essentially indicate where the objects are as per the other camera. And then you transform them into the coordinate space of this camera, and you do what's called late fusion. When you go to the non-maximal suppression stage, you say, I can see an object with 70% certainty, but a collaborating camera is telling me there is an object here with high confidence, so I should boost my confidence. So that's one approach where you do not modify the inferencing pipeline. An alternative approach is you train and create a new, so this requires a training, where you provide the inputs at the input itself. So you get one image, 3 channels of RGB. Maybe you have 2 collaborating cameras, you get 2 additional channels of black and white bit masks. And you train yourself so that you can detect objects more accurately. So on a PETS data set, again, I'm skipping a lot of details. You're welcome to talk to me or Ela afterwards. What you see is that this collaborative with training as compared to a basic baseline improves accuracy. The inferencing time slightly increases because you have to pay the network overhead of transferring these states between the cameras themselves. So this is what I'd say most unimaginative or the most straightforward way of doing collaboration. So let's move to the next stage, which is I have a single vision sensor, just one camera monitoring a space. Can I improve its energy profile in terms of using edge-based DNN execution, but using it in a smart way? So we look at this camera, which will transfer its captured images to an edge server where the inferencing models are executing. I should point out that almost my entire talk is about runtime inference optimization. It is not about training of models. That's not something that I work on. So with this, the idea is that if I can do a very quick early sensing, that in any image there is a region of saliency. This is where the objects of interest are going to lie. Then I am going to transfer these pixels at a higher resolution. The rest of the image, which is arguably less interesting, the background, I'm going to transfer at a lower resolution. So what I'm saving over here is not the sensing energy, I'm saving the communication energy of transferring this image over to an edge device. Now there are 2 types of prototypes of image distributions based on the type of applications. One is what I call uniform distribution. You have objects scattered all over the field of view. The other is it's skewed. There are objects only in some localized regions of the space. So what you need to do for this is have some quick and dirty method of on a per frame basis evaluating where the salient regions are, and then figure out ways to reduce the pixel budget that you allocate to the non-salient regions. So again, just through the animation, so there'll be a lightweight saliency estimator followed by a resolution adjuster on the camera. And then on the back end, we don't modify the DNNs. We take the images as they are, and we see how accurate then we can get. So again, we actually use a HAR feature-based object detector. This is just details. Because the scene is not changing that dramatically, you don't need to execute it per frame if you're doing 30 frames per second video. But you can do this periodically and save energy. But one of the insights why we're doing this, in terms of determining the saliency, when you see DNN execution, you see that whenever objects are smaller, the DNNs are less confident about them. So when objects are larger, there's greater confidence. This is sort of a typical operating characteristic. So what we do is, again, I'm not getting into the details. There are 2 types of algorithms. We look at the image, and we can use either a max-min optimization, which is I split up the image into, say, 8 regions. And each region, I keep giving it some pixels and see how its accuracy is improving. If it doesn't improve, you pick the weakest guy and you boost up the number of pixels there. Or you can use a water filling approach, which I guess some of you know, which is you try to equalize. So in the water filling approach, the buckets are the regions. The fluid is the pixels, the number of pixels you allocate, the resolution to each bucket, and you try to do it as to equalize them. And what this graph shows, this is the accuracy, the mean average precision score. This is the energy of the sensor itself. And you see that uniform resolution, if you increase resolution, you increase energy and you get higher accuracy. You can also do this with image encoding, but with the 2 water filling and max-min algorithms, for the same energy level, you get about 15% boost in energy. Or with the same accuracy level, you can reduce the energy by about a factor of 2. So reduce it by a third. So this is an interesting approach, according to me, where we're adaptively modifying based on the output from the DNN and using it to modify the sensing and transmission behavior of the camera. So that's a single camera. So the next piece that I'll talk about, what can we do? Because typically when we talk to campus deployments, there are cameras deployed, and these cameras are not partitioned. They have an overlap. There are lots of cameras that have overlapping fields of view. So the question is, there's clearly redundancy among these cameras. So the research question is, can we exploit this redundancy to reduce the sensing energy without compromising the inferencing accuracy? Okay, and so the idea is, of course, the answer is yes, but here is the basic idea. You have two cameras. The gray area is the field of view. So the way you can determine we can actually have an autonomous way of doing this. The two cameras detect objects, use object re-ID, and sort of progressively build up independently what they think is their area of overlap. So there'll be some errors. You will under or overestimate the true overlap. But once I have the overlap, the key idea is that in the regions that both of us can see, it's like this. If you and I, you as the audience member and I, are seeing the same object, but our eyesights are not very good. We see blurred objects or lower resolution views. But when we combine our disparate views, we can actually recover with as much precision, at least for object detection. There'll be cases for other types of tasks where this is not applicable, but we can deduce with the same level of accuracy, recover the same accuracy, but with lower resolution. So this idea, which we call collab DNN, is illustrated over here. And these two graphs are perhaps first the important ideas. So two different data sets you might be familiar, Wildtrack and PETS, are two different. This is an HD resolution, native HD. This is a much lower resolution. But if you look at the lines, and I'll just point to one, which is if they operate independently, which is the base, and you reduce the resolution, then the average precision drops dramatically after a point because the image gets blurred. On the other hand, if you combine the two blurred objects and you use a DNN that processes both images from two different cameras, both operating at low resolution, the drop in average precision is much more marginal. It's hardly a drop even when you drop to 128 by 128. And compared to 1056, that's a 10 times 10, 100-fold drop in the number of bits you're transferring. So again, without getting into the details, we have ways to figure out this overlapping area. The advantage of the scheme depends on how much overlap exists. Clearly, the more overlap, the better we are at exploiting it. But in real systems implementation, etc., we find that we can save about 30 to 40% energy overall with almost negligible drop in accuracy. Now, there are some details in the hardware. This was done on Raspberry Pi. There's some fine-grained hardware control we cannot do on the Raspberry Pi. If you go to more programmable, more sort of exotic boards, then you can get upwards of 40 to 50% energy savings. So one of the questions you will naturally ask is, okay, we talked about overlap, and so that's sort of this approach. But another approach, why not just partition the views? So you have this area which is A intersection B common. Let one camera handle that. The other camera just reduces its region of monitoring and just monitors its exclusive area. And then, of course, you have the independent. Both do it. But you'll see that for reasons that I won't get into now, so this collab cam approach ends up getting sort of operating here. Reduced energy consumption and reasonably high accuracy, whereas a partitioned approach, yes, you reduce energy consumption, but you see a significant drop in accuracy. So again, let me just go back for a second. What I wanted to reiterate is this notion that if there is a shared space with some spatial correlation, you don't operate independently. You actually get benefit by exploiting this mutual information present from different objects. Now, can we expand this further? So in this case, I have the same two pipelines between two cameras. So earlier what I talked was we could either exchange raw images or we could do the late fusion. But both of these approaches, the issue is this takes too much bandwidth, network bandwidth to transmit. Over here, the improvement is marginal. So the question is, as these networks execute, this is a pipelined process, can I do a transfer of hidden layer state and improve the accuracy? So that is this idea of POM AI, where I take feature maps from even the first or second convolutional layer. There's no end-to-end retraining. I run it through a simple machine learning model, which is a runtime model. And what it does is it transfers confidence values prior to the softmax layer for different bounding boxes or anchor boxes in the terminology that we use over here. So the idea here is that even looking at the very first early feature maps of large. So the key property over here is that when across these two cameras, objects that are closer to me will appear larger to me. I'll be more confident, but they'll typically be smaller for you. So I'll be transferring my confidence and boosting up your confidence. And because I do this in pipeline fashion, it's a non-blocking architecture. There's no difference in, there's no processing delay, etc. being incurred. Now there are some details here. You have to find the right feature maps. These feature maps are object class dependent. So if you are doing, say, human detection and car detection, you have to do two independent feature map transformations. But again, I'm not skipping those details. But what was surprising, at least to me, was that the accuracy, even with a simple gradient boosting machine, with a single discriminant feature map, is so high that it can predict the likelihood of objects in anchor boxes in a collaborating camera pretty accurately. And again, I won't get into details, but this general concept applies to a variety of object detection DNNs. It's not model specific. So here is ComAI is what I call the superior performance. So what this is allowing us to do is that you have these simple models that are, SSD, for example, low latency. Then you have YOLO v3, YOLO v4, high latency, very complex models, give higher accuracy. So we use simpler models like SSD, but we can boost their accuracy while maintaining low latency. So again, this is hopefully is an illustration that we are able to improve the efficacy of edge processing by collaborating among devices. The other important point over here, and this I'll allude to this afterwards in conclusion, is that the overhead of data transfer, the digest being transferred, is very low. It's 1 kilobyte per frame across the network. So we can even reduce this even further. So it's a very parsimonious collaboration system. Now, the last piece I'll talk about, and my student Ela is here, this is her work. So another way to reduce the edge network latency is this. You have all these cameras, they're overlapping or not, maybe not for now. They all transfer to an edge device. This is the edge node. What typically happens, suppose 4 cameras are sending 1 frame every second. You're going to run 4 instances of the DNN, each processing 1 camera's input image. What we want to do is just use 1 DNN, stitch the images from these 4 cameras together in some composite image so that we reduce, say this is 100 by 100, so we have 400 by 100 images. We'll reduce them to a single 100 by 100 image, process it with only 1 instance of the DNN. So that's reducing the latency of processing, but it's also reducing the memory requirements, etc. on the edge device. So the key question is, can we stitch them together? So earlier I talked about a single camera operating and adjusting its sensing resolution. What we are talking over here is, again, break up an image into a variety of tiles, but really focus on this last piece. So an image can be viewed as consisting of 8 tiles. Now we're going to fit these tiles at different resolutions. So here is the basic idea. Let me just show it visually. So here are, say, 6 tiles. There's some overlap because you want to capture objects that may be straddling the boundaries. So I've created 6 tiles. I'm going to apply 2D bin packing algorithms to fit these things with the right scaling and aspect ratio. There are lots of details that matter, but they're sort of second order details. So I fit them into this image. And the way we do that, we borrow a technique which has been used sort of in visual display literature called squarified tree maps. So you keep giving as many different regions, and it sort of packs them into a 2D region by rescaling and resizing individual objects. But that's just a method. You can come up with other methods as well. So does this work? So the reason this kind of works is you start off by looking, I go back to the thing that objects which are smaller, they actually have lower confidence. So we kind of classify them into small, medium, large objects at different resolutions. And what we do, this is just how the thing looks like. Instead of transferring this image, you transfer at different resolutions, which is the work I alluded to earlier. And then what you do is you stitch them into this mosaic. So you see these objects here, they have been given more space because there are many small objects. The foreground regions, which have likely no objects, they're very pixelated and have lower space here. So we fit them in. And what this allows us to do, so the baseline, you can see that the smaller objects have lower confidence, higher objects have higher. By adjusting the sizes, you actually equalize the confidences. So you can begin to see lower objects and medium objects get boosted, large objects lose a little bit, but that's okay because large objects will be detected anyway. What I've just shown is work just on a single camera, but now you can expand this. You have 10 cameras, let's say on a car, you have 10 camera views being processed by a single device. By using this querified tree map, by using hints of where salient objects are and the typical size of those objects, you can pack them into a single DNN and process them simultaneously. I will not get into those details because I want to wind up now. Looking towards the future, I think there are two issues that we should consider. One is this network adaptive AI. So collaboration is not just about information sharing. The other resource, it's not just the edge node. The other resource is the network bandwidth, the network constraint. It's in terms of energy or bits per second bandwidth. And we need to sort of find the optimal combination of both. And this may involve restructuring the network, because you can do that with beamforming algorithms, etc., to change the virtual topology of the network, but also use this, jointly optimize this with the level of collaboration that you do. The other interesting thing that I wanted to pick, this is a problem that really intrigues me. You know, the example I showed here is an example of spatial bin packing. But you can also do this not just per frame, you can do this across frames in temporal sequence. So you have A1 and A2 two regions and B1 and B2, and they keep coming. So in any one instance, you can process them in the following frame. Here you process all four. In the next one, you don't process region A2 at all, but you give more space to B1, B2. In the next frame, you process A2 and skip B1. So what this does is sort of an information-aware scheduling algorithms that are interesting as possibilities. So the last slide that I will talk about is, what does it mean for this notion of what I call a cognitive edge? I just gave some instances of projects and sort of key ideas. But as I look at the edge today, the edge is really focused mostly on acting as a computation offloading with partitions and containers to isolate devices. But I think the cognitive edge of tomorrow, the edge is an enabler of this collaborative machine intelligence. So it will allow devices, so for example, 5 bicycles riding together, maybe an edge on one of these will allow them to discover the commonality of their views, will allow them to establish who should share data with whom, where should the processing be done, what the optimization should be. So the edge is not just an offloading service, but it's an orchestrator and discovery service as well. And I think that's my vision of the future. I'll just leave you to read the concluding slide. The main thing I want to highlight is for orchestrating collaborative intelligence, both among different DNNs executing on a single edge device or across edge devices, but also between the DNNs and the sensors themselves on the pervasive device, because we can in real time change the sensing parameters on these devices themselves. This requires some standardized models for distributing the computational state. That's something maybe we can discuss when we go to the fireside chat, and the need for edge platforms to be enablers and orchestrators of execution. So that's it. I want to stop sharing and hand it back. I am hopefully okay on time.
Yeah. Thank you, Archon. It is really an enlightening talk, and I think it has generated a lot of interest also. I see a lot of questions coming in the chat window, and I think almost 80% of them Ila has actually answered. And
well, I'm glad she's doing her job.
Yeah. So, but it's quite interactive, and if you can see the questions, if you want to add, you can just add more thing. But because I think we will not have any formal Q&A, just that matter of time. So in the chat window you can get it, but we'll just kind of get started with the fireside chat now. And over the next 40 minutes, maybe we'll just spend and debate on these different problems that we think that this area is going to crop up. So to start with, what I will do is actually, I think Archana has already talked about it, but our other 3 panelists, Bala, Venkat, and Rijurekha, I would just request them to give a very brief view of or a perspective of this topic from their perspective. That what they think of this, maybe a 2-3 minutes introduction based on what they are working on. So I would start with Bala. Bala, I can do that. So let's do that first, and then we'll go into some questions that I have for the panelists. I'll put that, and then we'll open it up for the audience. That's the idea. So Bala?
Thanks, Sarpan. It was a very, very interesting lecture from Sir. So many of the challenges what you have mentioned, especially for the intelligent edge engines functionality, and then from that, how do you really achieve the kind of the key points like low power consumption as well as the low latency operation, right? So bringing computing near to the data source, the purpose of doing that is the same for the edge. And then as we see that there are several edge types we see around. There is a device edge, sensor edge, mobile edge, telecom edge, these data center edge, cloud edge, and then industrial edge, and then many kind of category of edges are there based on the underlying technology, and then based on the application scenario, and based on the kind of the functionality that is basically being addressed on the verticals. And then, so with this diversity, some of our work I like to mention, especially in the device edge category. So device edge is specifically meant for edge computing for devices, like whether it's for a healthcare device, whether it's for a industrial monitoring the devices, or even kind of quality inspections, or any kind of even robots, and then even nanosat or my satellites also have this kind of onboard edge computing, and then have come into this category. So what is the constraint from where this major constraint on the edge coming in? So it is coming from the deployment constraints, that is how and then where this edge computing need to be deployed.
So Bala, one suggestion that can you come closer to the mic a bit, because it's slightly coming a bit muffled.
Oh, sorry. Can you hear better?
Yeah, it is better. Okay, thank you.
Okay. Yeah, so the deployment constraints is the major thing now, the form factor, that is what basically limiting the computing, storage, communication power, and those so on. These are the components need to be packed in, and then that is the deployment scenario is one major thing constraining that. So the functional and performance constraints are, as already mentioned, the latency, security, privacy, and then even the dynamic workload is also need to be handled at the edge level. So the other thing which Archon already has mentioned is that the DNN, deep neural network on edge, is a big challenge. So there are multiple approaches. You can go ahead and then build a highly efficient, small, compact network so that the task can be completed. Or several kind of approaches, as Archon mentioned. You can try out those techniques along with this DNN architecture, pipelining, parallelization, all those things. Another technique is model size reduction. So that is basically model compression. We take a large, well-proven network and then compress that thing and then appropriately. There are several methods to do that, and then to achieve a better compact network. So these are the major kind of approaches or concerns or key aspects of device edges, and what I feel. And some of the related activities, how do we address this? One is the power. How do you really achieve the power reduction even to the hundreds or thousandfold? So neuromorphic edges is one. The neuromorphic computing, which uses spiking neural network, is one promising area what we see. This is like the neurons that we know that neurons in the brain basically communicate using these electric spikes, right? So they use the same kind of techniques with the analog spikes, basically conveying the information between artificial neurons. And then this has the potential of reducing the whole power consumption a lot. And then this can also result into more compact networks and a very, very high density of neurons. So that is one major thing. We have done quite a bit of work there, and then we see that this kind of approaches can really give quite a bit of power advantage. Other challenges basically we need to see that edge acceleration or with integration. On the devices, we know that we use CPUs, RISC-V computer, RISC-V processors, TPUs, GPUs, even neuro control states or FPGAs, and then specialized AI chips, microcontrollers, and then neuromorphic chipsets, as I mentioned. So how do you really basically work with all, especially having to design, having an edge design space exploration, you need to basically work with all and then to identify the right design. And from that perspective, it's a big challenge. What kind of abstraction layers we need to do it, and then what kind of frameworks we need to have integrating them for the architectural or the design explorations. So the specific things now compacting from a research side, hardware-aware neural architecture search, and which will basically find out on the right and compact network that is required for this, training-free pruning, lottery ticket hypothesis. These are some of the leading methodologies for raising the compact DNN models. And the other is on the privacy side. So that is another challenge where how do you achieve federated learning? Multiple edges basically learn their own model learning from the whatever data they collect individually, and then basically the learned data is basically connected to a centralized node, which basically aggregates and then you generate a model. So this basically preserves privacy so that one in the data is never revealed to the another device. So computing in encrypted mode with homomorphic technologies is the other one. So there are a few items, aspects I highlighted here. Probably as we go forward, we could get an opportunity to discuss more. So back to thanks.
Thank you, Bala, and it is a very good, I think, overall picture that has come out. And there are some questions that has come in the chat box also, Bala. If you see, that maybe you can answer now itself, and some of the questions I have, will take it up in the Q&A session. So now I will request Venkat to just provide his brief perspective. Venkat.
Yeah, sure. Yeah, let me share some slides here. One moment. Yeah, and meanwhile, I really enjoyed Archan's talk and also Bala's perspective. So thanks for setting the context. My presentation actually will be much more high level. Do you see my? Do you see it?
It is coming. It's not yet visible, but yes, now it has come.
And I have to move this video window away.
You have those windows that you have to move out here.
Yeah. Let me do that. How do I move it out? 1 minute. Okay. Is it good now?
Yeah, it's good. Please go ahead.
Okay, good. Yeah. So I'm going to keep it pretty high level and also somewhat provocative, just so that it triggers some discussion and so on in the Q&A period. So I'll provide my personal perspective on edge computing and where I think it is headed. Again, I'm making clear that this is my personal views and not necessarily that of Microsoft, although I will talk about some projects happening at Microsoft. The perspective is entirely mine. Just as context, you look at the rise of cloud computing over the past couple of decades. We went from on-prem compute that was not shared in a global sense and was dedicated to local organization to shared compute in the cloud, right? And there are many benefits of it, and there is lots that's been written. But this is a pretty well-known paper, I guess, tech report from Berkeley that calls out a lot of aspects here. And in particular, they call out this notion of infinite computing resources without the need for any upfront investment and pay-as-you-go model, right? So these are some of the benefits of the cloud. Now, when you look at edge computing, to some extent, it seems like the pendulum is trying to swing back, where you're moving from the cloud and, instead of calling it on-prem compute, you're calling it edge, which of course is different. I know I'm simplifying here, but it's something that's close to where the user is and where the user of the device is. Now, in doing so, there is a risk of reversing some of the gains of the cloud, right? The idea that you have the shared resource, the statistical multiplexing, and if I'm not using it, you can be using it, and all that stuff. There's a risk that you're going to reverse some of that. I'm going to have some edge thing at my home or in my car, which essentially remains idle for half the day or most of the day because I'm not using my car most of the day, for example. So there are a bunch of things, and that's fine. But I believe that if you're going to reverse some of the gains, it has to be done for a good reason, right? For a compelling reason. And these are some of the reasons that one hears about. And I think, yeah, okay, sorry, my animation was messed up. So there could be other reasons as well. But I'm going to just touch on the first three: latency, bandwidth, and reliability. I think there's privacy, and I think Archan touched on battery and efficiency and so on in his talk. So there's a bunch of them. Let me just talk about the first three, right? So, latency is often cited as a reason for this. In fact, the paper from CMU and I think Microsoft and so on from, again, more than a decade ago on edge computing, this is Satya at CMU and others, talked about, I think, latency as one of the drivers of their vision of edge computing, or cloudlets, I think is what they called it. Now, much has happened since then, right? So the cloud, whether it's from Microsoft or Amazon or Google or anyone else, has grown to be really huge, and it's got a truly global footprint. It of course doesn't have a footprint that covers the entire world, but this paper from a couple of years ago from Hotnets, did a measurement study with some existing data sets and made the point that the cloud is already close enough for majority of the world's population, and I think they said 20 or 30 milliseconds. I forget exactly what the number is for a huge fraction of the population. And so edge computing is likely to be only applicable for certain application niches. So their message was that latency as a motivation for moving to the edge is not as compelling as it perhaps was a decade ago. It's not that it doesn't make sense, but it has to be carefully justified. It probably makes sense only in niches. So, for example, if you were to consider something like a self-driving car, which is an extreme application, a critical application. If the car is going at 100 kilometers an hour and the round trip time latency is 30 milliseconds, which I think covers much of the populated world now, to the cloud, the car only travels about 0.8 meters in 30 milliseconds. And so if you need to control the car from the cloud, it's not such a bad thing. I mean, 0.8 meters, you don't need to you have to steer a little bit, but, it is quite doable, right? So latency cannot be a reason. There could be reliability and other reasons. I'll come to those, but, latency can't be a reason for many of these applications. And, latency is only getting better with 5G and with LEO networks and so on, right? So in some sense, the latency as a motivator is becoming weaker. Of course, there are applications like, wearables and AR, VR and assistive technologies and so on that interact very directly with a human or with the user that perhaps require latencies that are sub 30 milliseconds or sub 20 milliseconds. And so I think those are the niches that this paper also perhaps refers to. The second reason I'm going to touch on is bandwidth. Bandwidth, of course, has also been exploding, but one could argue that content has been growing even faster, right? In particular, video and 360-degree video and this and that and so on, right? So here, I will just provide a perspective on a project that I worked on. It's a project called HAMS, Harnessing Automobiles for Safety, where we had if you can see this here, there's a little smartphone on the dashboard, on the windshield, that's got all its sensors, looking at the driver, looking at the road in front and so on. So it was a safety kind of application we came up with. But the particular thing that we really took forward was automating the driver license test. This was actually, this has been rolled out at multiple RTOs across India and more in the pipeline. And there's a bit of a slowdown because of the pandemic and so on, but close to 30,000 automated tests have been done using our system, right? So it's a pretty nice thing, and our CEO talked about it a couple of years ago when he came to India and so on. Now, it turns out that during a test, we're using the front camera of the phone, the back camera of the phone, and other sensors. So we generate about 350 megabytes of data in a 10-minute test, which is not a huge amount, but it's a fair amount of data. And these RTOs are typically in locations that don't have great connectivity, right? And even if they have connectivity, it's down half the time, right? And so you can't, have a licensing system that says, oh, you can't take a license test today because the internet is not working, right? So we needed edge. We needed to process all this on site. And so because of the absence of reliable bandwidth, we had to do this. We actually worked a lot on sort of taking our algorithms and squeezing them to run on a phone, and we wrote a bunch of papers on it. But when it came to deployment time, we had to run this in places in North India and so on, which get really hot in the summer. Our phones really started melting down, right? They got hot with the front sensor and the back front camera and the back camera and so on. And so our edge was really not the phone itself, but an on-site server sitting in an air-conditioned room or at least a cooler place in the RTO that would receive data from the phone wirelessly and do all the processing and produce a report, right? An automated driver test report. And if you're interested, you can go to this link and there's more information on this project. The third and last one I'm going to talk about.
For time, can you just finish in another minute?
Yeah, very quickly. Yeah. So reliability is another reason, and I think reliability is something that is potentially quite compelling. For self-driving thing, even if you have latency and everything solved, you can't depend on a wireless link to get to the brain of your car, right? If the wireless link for whatever reason doesn't work, your car might crash. Another such example is sensing quality. So there's a project my colleagues have done called Dependable IoT, where if the sensor is producing bad data, then everything else you do is useless, right? It's completely junk. So you need to check the data that the sensor is producing right where the data is being generated. So that's another place where we put intelligence at the edge to do this. And this is being productized as something called Azure Verified Telemetry. You can look it up at this link. I'm going to skip this one. So there is work where you need to actually push to the edge. There's a bunch of work on taking ML models and shrinking them. But what my colleagues have done is actually built models from the ground up, taking into account constraints like memory and so on. So a model that will fit in 5 kilobytes of RAM, for example, right? And there's a bunch of applications. So this is my final slide. I think there's a lot of hype around edge, so we need to be careful about that. We need to be really clear on why we are choosing edge for a particular context, and then if if the context is right, then edge can certainly be a win, right? But we just need to be careful. So that's my point. Thank you.
Thanks, Venkat. And I think your last slide actually sums it up very well. And I think we'll revisit this in some of the questions I have actually.
Yeah, I don't know how to stop sharing. Oh yeah, stop sharing here. Okay, good.
And before we start, I will just request Rijureka to just a couple of minutes share.
Yeah, I don't think I have anything to elaborate because Archan has, both Archan and Venkat are my teachers. So I do more of what they are doing and only at scale at Delhi, and the same heating problem and those things come up. So I think we can go to the question so that we get more time to that.
Thank you.
I think Raju is nice because of the time that people like me ate up. She's giving
Anyway, I think that's good. So I'll just move into the questions. So I would start very briefly with Bala and Venkat first, that I think you are coming from the industry. So I think where do you see, like when you're talking about, yes, there is a lot of hype in the age and a lot of other things are there. So which are the industries, or where do you see this market for the next 2-3 years, where this age will actually go and where it will actually be needed from the market perspective, from the industry perspective? So Venkat, you can.
From an application perspective.
Go ahead, Bala.
Yeah, Bala. Anybody?
Oh, sorry. From an application perspective, what I see is that there is a lot of traction on edge in IoT application as a whole, more specifically in the predictive maintenance and then monitoring of machines on the machine floor. And we see quite a bit of activities and then requirements there specifically coming up. And there are other areas like utilities and for the kind of condition monitoring and some of such applications. There are also quite a few cases coming up in the healthcare as well, specifically on remote care and remote devices connected, and then for health monitoring, wellness monitoring, and then some of those kind of applications. What I see is that some upcoming areas increasingly in robotics is one area. Where recently also we have demonstrated over a teleoperation of the robot over 5G, and then how we are able to do that remote teleoperation very smoothly with the 5G kind of capabilities, and at the same time they also have some kind of intelligence in a shared autonomy mode, where human intelligence plus the robot intelligence basically used there. There what we use is that you have, as we know that now robots have multiple loops of control. One is in the inner loop, basically looks at very high sampling rate, the immediate control of the motors. And then there is a second level and outer loop. And then the third level is basically comes sometimes in the supervisory. All these kind of different time scales or can be or is planned at a different computing device. The inner loop is in the inner. So what I'm telling from an application perspective, IoT as a whole, and the second is in the robotics is coming up. And the third thing, if I want to mention, is that slightly far away, but still is basically in the satellite area. Intelligent satellite technologies where nanosat, small sat are exploding in the space, and then that is another area from a futuristic perspective. Thanks.
Thanks, Bala. And Venkat, you want to just add anything on top of it?
I'll keep it very brief. I think a combination of AR, VR, and wearables is one where I think both the latency requirements and the bandwidth requirements might be such where significant edge computing would make a lot of sense, right? And I think that I do definitely see as an area.
Okay, thanks. And then now I can kind of let us move back to some technology side of it, because I think Archana started and with this perspective of this conflict, Venkat also mentioned it. So, one side we told that, okay, we can do everything in the edge, and then the low latency, privacy, everything is there. And on the other side, 5G and everything is promising that, yes, I don't need it. That Venkat was also. In reality, they're telling that, okay, I can actually use the cloud and there's a really low latency. I can do a lot of things using that kind of a system. So what I want to kind of ask, and that, are we kind of, there's a point now to look at this holistically, like this, there is a communication, there is a intelligence, and there is actuation. So these are three things that are happening together. And is there a need now to look at this at a holistic together, instead of looking at one part or other and do a kind of a joint optimizer or something? So this is one part of the thing, that how that stack will look like, and what the role of the security and privacy in this. So I think these are the two questions I have, and I would request Vijureka to start, actually. So, and then maybe we can hear from others.
Yeah, so there is a large difference based on where we are doing the work. So like the way 5G, 6G and those things are rolled out in some countries, there is definitely a latency things get developed in India or get deployed in India. Even with 4G, when we are, as Venkat is saying in his RTO, similarly when I deploy sensors in Delhi buses or in highways in the truck around Delhi NCR, even 4G signal is not that well covered at all locations. So this as Venkat is saying, it's always a thing that what is available where and what problem we are trying to solve. There we see that whether network is available, we can use it. If it's not available, what is the fallback option? And if it's safety critical, then we have all the compute resources in hand. If it's not safety critical, for example, I do air pollution monitoring. It's not safety critical, but it's important to monitor it at certain latencies. And also there is nothing of edge computing there. It's more of sensing and aggregating it. But after the aggregation, a lot of analysis is happening, which is happening essentially at the cloud. So there are interesting questions of privacy again comes up, which is not expected, because air pollution is not something which we thought that will be privacy sensitive in any way. But it happened that when I deployed sensors in Delhi buses, there was this Ola cab companies which came to me saying that they wanted to do this sensor deployment for as a CSR thing, as a corporate social responsibility, but they were very sensitive not to share their location traces. So where their cabs are going at what time of the day, this is very sensitive information for their company. So this is the problem is like that there are multiple fleet companies which all can take part in this edge scenario where they're sensing data. Now things are getting aggregated either in the local servers or in some central place, but then the queries that we are asking that has to be privacy preserving, or the interpolation model or forecasting models that we train, which involves data from all these companies, that also has to have some privacy preserving machine learning techniques used. So this I mean there is I don't know exactly where this will go or anything in the future, but at the moment, the way I look at it is look at what network resources are available for deployment. And then if there is a privacy or some concern which is coming up, handle it using whatever crypto tools are there. And of course, again, crypto adds some more burden of computation at the edge as well, because it doesn't come for free.
Okay, thanks. So anybody else wants to add anything? Bala, Venkat, Archan?
I can just add one thing. I mean, I think with regard to privacy and security and so on, I mean, there's a lot of advance in secure computation, right? So where you can operate on data that is fully encrypted. Of course, there is significant slowdown, but it is getting to the point where for certain critical applications, it is practical, right? And there's work in our lab and in a bunch of other places. So,
yeah, so this particular thread, actually Divya's group and I are collaborating, because
correct,
this is a nice use case where
yes.
because their model is very slow, but pollution is not a critical application. So that's where
Yes.
it
So
might be.
Divya, Gupta and others in our laboratory, of course, there are other places also there's work that's happening. So I think, we may be able to do computation in the cloud that is just as secure and as private as, anything else.
So,
Okay, thanks.
if I can
Yeah,
add
Archan. Yeah.
very brief response, not specific examples of the kind that Riju cited, but I think, in my view, the opportunity for the edge still persisting, even when 5G, etc., comes along, is the need for closed loop, real-time control of the sensors or actuators themselves. And in particular, when I think of something like a LiDAR-based sensor, it has very high energy consumption, generates a huge amount of 3D point cloud data. So we can probably filter away and use saliency approaches to deactivate the sensor or throw out, discard a huge percentage of the data right at the sensor node itself. But for that, you need a very tight time constraint in doing the analytics and feeding it back. And I think that's one case where, especially if you have lots of these type of devices, maybe robots, autonomous robots moving around in a warehouse and so on, that's an area where jointly designing the network itself, sort of laying out the parameters and deciding, what is the topology of the network, the wireless network, and the collaborative execution on the edge. I think that's a joint design opportunity, something exciting. Thanks.
Okay, thanks. I think so. I will just move to the next question then, and I think I would request Bala to answer this first. Is that when we actually did distributed computing on cloud, the underlying hardware was pretty homogeneous. Okay, and now that we are moving into edge, it is still a distributed computing problem, and we are trying to do, but the underlying hardware, the heterogeneity is just humongous. That if you think about every camera, every device, every wearable, everything has a different kind of a thing. The CPU is different, TPU is different, memory capacity is different, clock is different, everything is different actually. So what is the new challenge that you see because of this? Now, how do we, when we deploy in this heterogeneous hardware, because the heterogeneity is actually the power of the cloud, but what challenges it throws up? That is the kind of, Bala, can you just throw some light on that?
See, from a development perspective, it's really challenging because the diversity of this hardware processors and even the sensors by themselves, and then that need to be focused on domain-specific tool sets are there, and then which make the optimized implementation with those tool sets. There are no generic tool sets which can work across with the kind of efficiency that some of the domain-specific tool sets are giving. So today, majorly the kind of approaches people do is that a microservices approach. So see the whole application as a graph. So you have an underlying graph model with the nodes as the processing, and then each of the processing you basically map it to the right hardware platforms, and then develop those microservices and have this in this graph structure. And then, but at the same time, if you want to look at implement the whole thing and optimize across, there are some approaches people have started exploring, like OpenMP is one thing, and then another is on then other things like OpenFL for FPGAs. And OpenMP is specifically looking at general purpose compute, CPUs and then GPUs. And at the same time, SYCL is there, SYML, right? SYCL is basically really a promising one where it's programmatically integrates multiple kind of platforms, hardware computing platforms, create this kind of thing. Though they are slightly far away from their vision, but that is something. These are few directions I'm really seeing it that handling these things in the integrated manner, and at that time being is basically on the microservices composition is something that's good.
So I just follow-up question, maybe just one in yes and no. I think everybody can give an answer. Do you see standardization playing a role in this heterogeneous environment that is now cropping up in edge?
Yeah, from my perspective, yes, the standardization there's in the edge area, but at a higher level happening with the MAC, the multi-edge computing standards, and 3GPP is basically working on standards, and another one MAC is from HC. But on the devices, but the kind of problems, multi-heterogeneous devices, it will be very difficult to standardize that. We have seen it in IoT also. And but there will be some emerging players coming in, and then they basically come and make the standards. Otherwise, this kind of integrative approach will basically go with the appropriate envelopes built on that.
Okay, thanks. So any quick comment from Archan, Venkat, Rijulekha on this? Or I will move to the next question then. Okay. So now the next question that I have is more of a more fundamental kind of a thing. Like, that we had from old time, we had our embedded systems, cloud computing, distributed computing, but subjects are taught in computer science. And today, kind of, sometimes I see edge computing being taught as a mixture of these three. As a computers, when you look at the computer science kind of a thing. So what is your take? But I think I'll start with Archan. That how, if we think of edge as a concept, so how we should treat it differently than just treating these three different separate subjects separately?
Just trying to unmute. Okay, so I think that if the question is, are these like fundamentally different problems?
Or I would say that is it edge computing is more than just these three?
Yeah. So I think, first of all, I don't think they're fundamentally new problems. Like the example of 2D mosaicing or bin packing. That's a scheduling problem, but in general, these are problems of resource optimization, weighted scheduling, etc. So they're classic system problems. I would say the notion of distributed execution, again, just as a thought, the distributed execution is, there's a lot of work on distributed in-network processing in wireless sensor networks. Execution was modeled as a DAG, and the only difference is there was a multi-hop graph, but here it's maybe more a hub and spoke network topology. But perhaps more than just maybe distributed computing or I would say sort of cloud computing, the one possibility that I think of is this notion of maybe a hierarchical notion. Again, haven't done any work on it, but I keep thinking of this notion of hierarchical layers of AI logic or DNNs. Where, so for example, upper layers would extract logical concepts at slower timescales. So, you have cameras, say, monitoring wildlife or something. And so an upper layer collaborating with other camera nodes will say, oh, now we're more likely to see leopards because the leopards are moving in, and it's not going to be elephants or poachers. And that will allow the lower layers to then take this notion and optimize themselves so that they can detect leopards with higher accuracy, with lower energy and faster, things like that. So the one possibility I see in this is this notion of a hierarchical decomposition of AI-based tasks. Right now, I seem to see either what I call a pipeline. So it's like sort of one AI pipeline feeding into another AI pipeline, or just totally independent, isolated per task. But this notion of a sort of multi-scale execution of AI pipelines, I think, is a new problem that edge computing may bring in. And I'd love to hear any opinions from the other panelists on this as well.
Yeah, Venkat, any thoughts?
I completely agree with Archana that these are all names, but they're not fundamentally different. Like even cloud computing, uses a lot of principles of distributed computing and and so on. So I don't think they're fundamentally different. I think it all boils down to this is engineering rather than science, right? What I mean is, though we call it computer science, it's really working with constraints, right? And the constraints here are whatever a particular application, like where you talked about pollution monitoring with buses and cabs and so on. So there are certain constraints, and then you have to sort of figure out where the bottlenecks are, and then attack them. So, for example, one area which has seen a lot of interesting work is in some applications you do need ML models, powerful ML models, to run at the edge, right, for various reasons. And so, how do you then take these models and shrink them or develop them from the ground up as compact models, and have them be accurate and at the same time have a really small footprint, right? So lots of very interesting work, cutting edge work happening on that. So likewise, for any of the other things, once you identify where the bottleneck is, if it's network bandwidth, maybe there is sort of techniques, networking techniques that can be used. So I think if you identify where the bottleneck is, I think research problems will come out of it, but they are driven by the constraints and the context, right, rather than fundamentally new, I would say.
Okay, so yeah, thanks. Yeah, did you please add it? Yeah, please.
Being a teacher at IIT, the thing which I try to use in the courses is use examples from edge computing in all the courses, because somehow strangely in a data structure course, in a computer architecture course, in an operating system course, there is no course where I cannot introduce a concept or explain it, because an edge device is essentially having different kind of coprocessors which are very useful in defining an architecture course. Then the operating system is either Linux or whatever, and it has to do a lot of scheduling and paging and those things. So if and that way the students are also more connected in seeing exactly that the theoretical concepts they learn in the class, what is a kind of a use case or what is a device. If we take their mobile phone and say that these are the things in the book which are running in these contexts here. So I don't really feel that there is any new subject which needs to be introduced and taught as a set of concepts. Already we have the courses. It's more of connecting things like that. I have put a link here of a grad level course which the other attendees can look at, where I take this edge computing, the DNN models running at the edge, and then I say that at every level there are being optimizations. There are architecture people coming up with neural network architectures, there are system optimizations happening, then there are smaller ML models, and more on scheduling. So it's like having this like full stack thought process is very useful in any edge when we are building. As Venkat is saying, we do engineering, and as a good engineer we should know about the full stack. We shouldn't say that I know only the OS, I know only machine learning. So this sort of interdisciplinary thinking within CS is very useful.
I think thanks. And so
One liner I would like to add is that the multi-target compiler could be a compiler for edge systems is a good topic, where write one program and it basically runs on multiple targets at the same time and based on the configuration. So that is something from a CS problem perspective I would like to suggest.
I think that's a very good idea. So Professor Chitra, can we just extend this by, we are already kind of 7, so another 4-5 minutes if it is there. I would, maybe there are a couple of questions that have come from the audience. I just wanted to ask that to the panel. Would that be okay?
Yeah, definitely. Yeah.
Okay, so I think that what we'll go back. So there are 2 questions at least that has come in the channel. So I'll just ask that, and anybody can from the panel can pick it up. And the first question has come from Karthik Narayanan. So I think what he's telling is that if we do all the things in the edge itself up to analytics, how enterprise can get feedback from the end user. And this end user, sometimes this feedback is important for the business.
I can maybe take a shot at it. I mean, I think, at least in my view, whether you do the computation at the edge or the cloud or somewhere else, which entity owns the data and who has access to data? I mean, that's a slightly orthogonal question, right? Like, you could be some corporation that produces phones, and now you have access to the data, even though it's on the phone, right? I'm sure Apple and Google and so on, they have a lot of access to a lot of data, right? So I don't think the edge versus cloud versus some other place has a direct bearing on whether you have access to data. That's an orthogonal question. At least that's my view.
Yeah, I think this is very application specific, and that's what it is. The data will go where it is supposed to go. I think that is what, if it is needed to go.
I'll give you an analogy, and this is something that I see many governments insist that the data of their citizens be within their geographical boundary, right? But if you think about it, these are all encrypted bits, right? My file could be on my adversary's computer or server, but it's a bunch of encrypted bits. They can't do anything with it. Yeah. So in some sense, and just because the encrypted bits are in my within my geographical boundaries doesn't mean I can do anything with it, because it's all encrypted. So unless I have the key, I can't do anything, right? So I think it's kind of somewhat analogous to that. The location and access to data are slightly separate questions, I think.
Yeah, I think that is right.
If I may just add, I mean, just echoing, actually want to pick up on something Venkat, when he described some of the work at MSR. The one thing we need to pay attention to is, because the edge does analytics, and effectively we're saying we're throwing away the raw sensor data. But the reality is that, sometimes there will be either errors in the sensor data itself, or there will be concept drifts. So I think there will always need to be at least a trickle of data that goes back for sort of self-monitoring and diagnostics on the analytic algorithm themselves. So we can't completely abandon it, because then it's like we won't know what we don't know and what's wrong. So I think you need to guard against that. So there has to be at least a small pipeline that allows even the raw data to be going back to the backend cloud for analytics purposes.
Yeah, I think that is important, because if what edge throws away may be useful for something else. And I think that is a point. So I think there's one more question. I think we'll end with this question, very quick answer maybe. So there's a question from Deepak that there is a lot of talk of hierarchical computing layers with fog computing. So what is the future of this paradigm in real-time system deployments, real system deployments, rather? So Archana touched upon it, but maybe more specifically, anything you want to add, any of it? So I think what is meaning is that in the real system deployment, how close or how realistic it is really to this hierarchical computing to come. I think that may be the meaning of the question.
So Arpan, I'll take a stab, but I think this is a question that either Venkat or Bala would be better, I mean, with their sort of industry insights, would be better prepared to answer. But again, my personal opinion is, I mean, just overall architecturally, we either have one hop logical topology, or we have a two hop. I mean, for the vast majority of systems. So this notion of, say, 3 layers of, a fog type network, where there is some edge device, then an intermediate device, then a secondary intermediate aggregation, then a big cloud server. I'm personally skeptical of that. I don't see compelling business reasons for it, but a lot of that is my ignorance. Having moved to academia, I can be blissfully unaware of the real world.
So Venkat, Bala, anything you want to add? And then we'll continue.
One thing I would like to add is that yes, there are no situations. For example, in our own experience itself, even monitoring, in a steel plant, a person, the operators need to work with very, very challenging environments, like in blast furnaces, and then their health need to be monitored, and then and then appropriately alert need to be generated. In case an alert generates, that need to be handled appropriately, and so the whole thing is a loop, and then that need to be even informed to some of the legacy applications, enterprise applications as well. So each of these things now reside at multiple levels. A wearable sensor detects an anomaly on on ECG of the person, and then that is through a Bluetooth which sends to the edge device, and then the edge basically finds out, the categorizes it more with a high confidence level and transmit it to the cloud, and then from the cloud, it basically gets integrated into the enterprise system, where this is the appropriate method of handling the whole thing happen. So many a time the sensors and then IoT or the edge application don't stay in an island. It basically integrates in an industrial system, and so it spans across.
Okay, thanks. So Venkat, any closing remarks on this question, and then we'll close. Any quick?
No, I think I kind of agree with particularly with what Archana said. I mean, I think there's certainly maybe applications where hierarchical approach would be required, but I think in general simplicity wins, and there's nothing simpler than just a hub and a set of spokes, right? So you have the edge, the sensor has to be where the user is, because that's where the user is, and the compute can be in one central powerful place, and you have good connectivity. If that works for your application, you should just do that. If that doesn't work for your application, yes, then you may require hierarchy and so on, but it has to be done with care, right? And I think Bala had some examples, and I think in those places it may make sense, but in general, adding hierarchy adds complexity and may not really be required.
Okay, I think thanks. I think we can continue this discussion maybe for another hour. So many interesting things, but I think it to close now because we're already 10 minutes over the thing. So I think thank you for everybody to joining this, and it was very interesting discussion. I think hopefully it does a lot of takeaway. And so I would like, so Arvind, Professor Chitra, you can just you can close. Yeah.
Yeah, Arvind, do you want to conclude?
Yeah. So thank you, everyone. That was a very interesting and informative webinar. So I would like to thank all the speakers who joined the webinar today. Venkat, Archan, Rijurekha, Arpan, Bala, Ila, and Chitra. So thank you all. Thank you to all the attendees who joined in for the webinar. And yeah, that's about it for this edition of the webinar. See you in a quarter's time.
Thank you. Thank you so much. It was a very informative and insightful discussion. Thank you, everyone.